Hi, good morning, students. So, this is the online platform once again. Welcome to you. So, in this session, we are going to be discussed about the applications of this is the online platform once again. Welcome to you. Okay, students, once again, good morning to one and all. So, today we will discuss the applications of second and higher order linear differential equations with constant coefficients. So, in this part, first of all, I will explain the one application, the method of variation of parameters. Today, we will discuss the applications of second and higher order linear differential equations. In this part, first of all, I will explain the one application, the method of variation of parameters. Okay, students, shall I start with the method of variation of parameters? Method of variation of parameters. So particularly this method is used to solve any given linear differential equation with constant coefficients which is of order 2. Means this method is particularly useful or used to find the solutions of only second order ordinary linear differential equations with constant coefficients. So let us consider the standard form of a only second order ordinary linear differential equation with the constant coefficients is d square y by dx square plus p into dy by dx plus q into y equal to r, called as equation 1. So here p, q and r all are functions of independent variable x. All are functions of independent variable x. So the standard form of a second order linear differential equation with the constant coefficients is of the form d square by dx square plus p into dy by dx plus q into y equal to r, where p, q, r are functions of x alone. Okay, so please remember this method is used to solve particularly only second order linear differential equation with constant coefficients. So in the examination, if any question is given on a particularly second order linear differential equation, so you may solve that question by using this method of variation of parameters. So students, you are already observed so many problems we did in our previous classes, so which consisting of second order. So you may try every second order linear differential equation with constant coefficients by using this method. Okay, so shall I move to explain what is the procedure to solve any given second order ordinary linear differential equation by using this method. So clearly it is a second order differential equation. So ultimately its a general solution may consisting of only two arbitrary constants, say C1 and C2. So we are using the usual procedure. So first of all, we can find its corresponding auxiliary equation. So may I write with the help of introducing the differential operator, capital D is nothing but d by dx. So few authors are used theta, don't confuse. Theta is also same with d by dx. But now I'm using capital D. So what do you mean by d square now? So d square is same with d square by dx square. So then equation 1 becomes as d square by dx square means capital D square y plus p into d by dx is capital dy plus q into y equal to r. So this is of the form, so d square plus p into d plus 1 into y, which is equal to r. Or say for our convenient, it is of the form f of d into y equal to r. So please won't confuse the students. So already we used the same notation for nth order linear differential equation with the constant coefficient is of the form f of d into y equal to q there. But here you remember that, please. What do you mean by f of d here? F of d is consisting of only second order, that is d square plus pd plus only 1. Now let us start with auxiliary equation. So auxiliary equation is written as f of m equal to 0. Replace d by m in f of d and equating to 0. So ultimately we get m square plus pm plus 1 equal to 0. So clearly it is an equation in m which is of degree 2, ultimately which possesses only two roots, ultimately which is having only two roots. So by making use of two roots, now let us ready to start write its complementary function. So its roots are 2. So generally whenever the two roots are either a real type of roots or a complex form of roots, generally we write its corresponding complementary function as like this c1 into u of x plus c2 into v of x generally. So already we know that if the two roots are real and equal, then we are ready to write its corresponding complementary function as like this, real and equal, c1 plus c2 into e power some ax atom. Okay, if the root is a comma a repeated. If the two roots are unequal, we may write what if a comma b are two roots, then we write its corresponding complementary function as like this, c1 into e power ax plus c2 into e power bx. So here a comma a are two roots, c1 plus c2x into e power ax. If a comma b are two distinct real roots, then we write c1 e power ax plus c2 e power bx. So in the case of a complex form, pair of complex a plus r minus ib, then we write its corresponding complementary function as like this, e power ax into c1 cos bx plus c2 into sin bx. So means if you observe all these cases, so generally they are of the form, c1 into something plus c2 into something. If you observe the first one, this is what c1 into e power ax, c1 into some function of x, c2 into x into e power ax, that is what c2 into v of x. If you observe the real and equal cases, c1 into e power ax, c2 into e power bx means generally what viewed as c1 into u of x plus c2 into v of x. The complex form also c1 into something plus c2 into something. So please observe, we are solving by using this method only second order linear differential equation. So what is our observation? Complementary function. So complementary function generally written as in the form of c1 into some function of x, u of x say, so c2 into v of x. So c1 and c2 are two arbitrary constants. Clearly u and v are functions of x. Means after finding its auxiliary equation and its roots, ultimately we know that complementary function is c1 into u of x plus c2 into v of x. So ultimately we know that u and v are, ultimately we know that u and v. So by making use of u and v, now we move to find u into v dash minus v into u dash. So what do you mean by v dash? This is a one-time derivative of v with respect to x. U dash is one-time derivative of u with respect to x. Okay. So suppose that u into v dash minus v into u dash is not equal to 0. Now, in order to find the two arbitrary constants values c1 and c2, so let us write its a corresponding particular integral. So particular integral of given differential equation is a of x into u of x plus b of x into v of x. So what is the abbreviation of ax? A is a function of x, b is a function of independent variable x. Already we know that u and v are clearly functions of x. But how we will determine the values of a of x and b of x? So we will determine a of x and b of x like this. Okay, so in order to find a of x, we use this formula minus integration of rx into vx divided by u into v dash minus v into u dash dx. And we will move to find bx value by using this formula integration of rx into ux divided by u into v dash minus v into u dash dx. So please remember once again. So after converting any given differential equation into this particular standard form, please observe the screen once again. First slide. So after converting any linear differential equation into the standard form, d square by dx square plus p into dy by dx plus q into y equal to r. So ultimately we know that r value, r as a function of x, means, so while computing a of x, we require a capital R. Okay. And after knowing its corresponding complementary function, u is known, v is known. Now what is a of x? A of x is involvement of r and v value divided by u into v dash minus v into u dash. And b is also same what, having a rx ux divided by uv dash minus vu dash into dx. Okay. So upon knowing a of x and b of x value, put in this pi. So ultimately we know that it's corresponding particular integral. And CF is known. Now we are able to write complete solution. Now we are able to write a general solution. So what is the general solution? That is the sum of complementary function and a particular integral. So complementary function so far, that is c1 into u plus c2 into v plus particular integral is a of x into u of x, that is au, b of x into v of x dv. Okay, so now let us start doing one or two examples on this. So first example, solve d square plus 4 into y, d square plus 4 into y equal to secant 2x. Solve d square plus y, d square plus 4 into y equal to secant 2x. Or it may be observed like this. They are given like this also, d square by dx square plus 4 into y equal to secant 2x. So compare with this equation with the general equation, that is compare with the general equation d square y by dx square plus p into dy by dx plus q into y equal to r. So what is our observation here? Clearly p is given as 0. So q is given as 4 and r is given as secant 2x. Okay, please remember, while any second order linear differential equation with the constant coefficient is given, first of all our duty is convert that equation into the standard form. Please observe, always the coefficient of d square by dx square should be 1. then only you consider R value. So before considering R value, you must see the coefficient of d square over dx square should be 1. Then only you write R value. Now R value is clearly secant 2x. So first we find it's a complementary function. First we find its complementary function. In order to find a complementary function, first write its corresponding auxiliary equation. So auxiliary equation is generally f of m equal to 0. So replace d by m. So indirectly, what is f of d here? So f of d is d square plus 4. So auxiliary equation is f of m equal to 0. We get m square plus 4 equal to 0. So clearly it is a quadratic equation in m. So it may be written as m square minus of 2i whole square equal to 0. Why? Because so 2i whole square means it is given by 2 square into I square. So 2 square is 4, I square is minus 1. This is given by minus 4. But before minus sign is there, minus of minus 4 plus 4. So we get right m square plus 4 as m square minus 2i whole square. So now it is of the form a square minus b square equal to 0, a plus b into a minus b form, m plus 2i into m minus 2i equal to 0. So by m plus 2i equal to 0, we get m equal to minus 2i, and m minus 2i equal to 0, we get m equal to plus 2i. So therefore, m which is equal to 0 plus or minus 2i. 0 plus or minus 2i. So now what is its complementary function corresponding to this pair of complex roots? So what are the roots once again? That is 0 plus or minus 2i, m1 plus or minus im2. So here real part is 0, imaginary part is 2. Then its corresponding complementary function may written as like this, e power 0 real part into x. Why? Because here clearly independent variable is x, independent variable is x. So we write complementary function as a function of x. So e power real part into x, 0 into x into c1 into cos of imaginary part 2x plus c2 into sine of imaginary part 2x. So since e power 0x is 1, so complementary function is c1 cos 2x plus c2 sine 2x. But please observe, in generally, complementary function may consider as like this, c1 into u of x plus c2 into v of x here. So for our convenient, so after knowing complementary function, that is compare with c1 into some u of x plus c2 into some v of x. So ultimately, what is u of x value here? So function of x, u of x is cos 2x. And what is vx? Vx is sine 2x. Okay, so let us check uv dash minus vu dash is 0 or not. Okay, why? Because uv dash minus vu dash both are present in the denominators of ax and bx. So uv dash minus vu dash is non-zero, then only the integration of right hand side of a and b are exist. So for the purpose, first of all, we must check u into v dash value minus v into u dash value. So now consider u into v dash minus v into u dash. So u is known as cos 2x. And what do you mean by v dash? V dash is derivative of v, that is d by dx of v of x, d by dx of now sine 2x minus v into sine 2x into d by dx of u, d by dx of cos 2x. So this is given by cos 2x into d by dx of sine 2x. So derivative of sine 2x is cos 2x into derivative of 2x is 2. So totally derivative of sine 2x is 2 cos 2x. So minus sine 2x into derivative of cos 2x. Derivative of cos 2x is generally derivative of cos x is minus sine x. Derivative of cos 2x is minus sine 2x into derivative of 2x is 2. So what? Derivative of cos 2x is minus 2 into sine 2x. So upon simplification, we get cos 2x into cos 2x is cos square 2x. Here minus into minus plus. So it is pre-multiplied with the 2 into cos square 2x, minus into minus plus 2 into sine x sine square 2x. So this is in the form of 2 into sine square theta plus cos square theta, that is 1. 2 into 1 equal to 2, clearly non-zero. Now let us move to find particular integral. How we will write its general particular integral? Particular integral is ax into ux plus bx into vx. So, but already we know that ux and vx respectively cos 2x and sin 2x. So now our job finding ax and bx value. So let us start with the first ax value. So what is the formula of determination of ax? So ax formula is what? Minus integration of r into v divided by u v dash minus v u dash, and perform this integration with respect to x. Okay, so minus integration of what is r value? So from the given differential equation, right hand side part is secant 2x. So r value is secant 2x into v. What is v value? V value is sine 2x. R is secant 2x, v is sine 2x divided by u dx form. Okay, once again it may be rearranged as half of minus sine 2x divided by cos 2x into dx. So now let us recall substitution method, f dash of x by f of x into dx. What is the denominator here? Cos 2x. What is the derivative of cos 2x? Minus 2 into sine 2x. But in the denominator, only minus sine 2x. You have to convert it into standard form, that is integration of f dash of x by f of x into dx. So we need to multiply and divide with 2. So 1 by 2 into 2, 4. Integration of minus 2 into sine 2x divided by cos 2x. So now please observe, what is the derivative of cos 2x now? Minus 2 into sine 2x. So it is of the form f dash of x by f of x into dx. So what is the formula of integration of f dash of x by f of x into dx? ln of f of x, ln of denominator, ln of cos 2x. So what is the a value so far? 1 by 4 ln of cos 2x. Now come to bx value, b value. So the formula is integration of r into u divided by u v dash minus v u dash into dx. So integration of what is r value? R value is given as secant 2x. U value is cos 2x divided by u dash minus v u dash is 2. Okay, so now simplify this one. 1 by 2 into integration of secant 2x is 1 by cos 2x into cos 2x. So cos 2x both are getting cancelled. That is 1. 1 into dx is dx. So now half of integration of dx is given by x. Means what is our value of bx? Bx is x by 2. So now a value is given as, so now we get a of x is ln cos 2x by 4 and bx is x by 2. So now write first particular integral. What is particular integral? A of x. So what is a of x value? 1 by 4 ln of cos 2x into u of x. So u of x value is cos 2x plus p of x bx, that is x by 2 into vx sine 2x. So this is particular integral for given differential equation. So hence now we are able to write a general solution. So hence general solution of given differential equation. One is a dependent variable y equal to complementary function plus particular integral. Complementary function plus particular integral. So already we know that complementary function is a c1 cos 2x plus plus c2 into sin 2x. Plus of particular integral is just above, that is cos 2x into ln of cos 2x divided by 4 plus x into sin 2x divided by 2. So this is the general solution of given second order linear differential equation, that is d square plus 4 into y equal to secant 2x by the method of variation of parameters. Okay, so this is the first problem on a method of variation of parameters. So let us move to do one more problem on this. Okay, second problem on this method of variation of parameters is solve d square plus 1. Solve d square plus 1 into y equal to x into sin x. D square plus 1 into y equal to x into sin x. So I think some of you already familiar with this problem. So already your teachers discussed this case earlierly also. So we will do once again, because this is a second order linear differential equation. This is a second order linear differential equation, that is d square means d square y by dx square plus y, which is equal to x into sin x, called as equation 1. So what is f of d? So f of d is coefficient of y on left hand side, that is d square plus 1. If it is compared with our standard form, that is d square y by dx square plus p into dy by dx plus q into y equal to r form. If the given differential equation is compared with this standard form, ultimately here p value is given as 0, q value is given as 1, and r value right hand side part is given as x into sin x. Okay, please, once again, in the given differential equation, the coefficient of d square by dx square is 1. The coefficient of d square by dx square is 1. Please remember, while doing any problem, any second order linear differential equation with the method of variation of parameters, you must observe, you must convert the coefficient of d square by dx square should be 1. Then only you consider p, q, and r value. But here we are must focus on only r value. R value is x into sin x. Now let us start with the auxiliary equation. So for finding complementary function, we need to write first auxiliary equation. Auxiliary equation is f of m equal to 0. This is given by m square plus 1 equal to 0. This is also similar with previous problem, m square plus 4 equal to 0. So here we get m square plus 1 equal to 0. Once again, this may be written as m minus of I whole square. M minus of I whole square equal to 0. What do you mean by I square value? Minus 1. So minus of minus 1 plus 1. So m square plus 1 may written as m square minus of I square. So once again, it may be written as m plus I into m minus I equal to 0. So upon simplification, we get m which is equal to minus I comma plus I. This is same with m which is equal to 0 plus r minus I. So please observe, this is 0 plus r minus like 1 into I form. 1 into I form. So what is 0 here? 0 is the real part and 1 is the imaginary part. 0 is the real part, 1 is the imaginary part. So by keeping these two parts 0 as real part, 1 as imaginary part. Let us try to write its complementary function like this. So complementary function is e power real part into x, that is 0x into c1 cos of imaginary part imaginary part 1 into x plus c2 into sine of imaginary part is 1 into x. So once again, it may be written as e power 0x is 1, that is c1 into cos of 1x cos x plus c2 into sine of 1x is sine x. Okay, now complementary function is c1 cos x but while solving the given variation of parameters, let us in the form of c1 into now. So here ux value is a cos x, vx value is a sin x. Ux value is cos x, vx value is sin x. So let us check uv dash minus vu dash value. Why? Because it's never be zero, then only a of x and b of x values are exist. So let us check the value of uv dash minus vu dash. U is cos x into v dash, derivative of v, that is d by dx of sin x, derivative of sin x is cos x, minus v sin x into u dash. U dash is derivative of u, derivative of cos x, derivative of cos x is minus sin x. So this is given by cos x cos square x minus into minus plus sin x sin square x. This is given by 1. 1 is not equal to 0. So now write its corresponding particular integral. So general particular integral is ax into ux plus bx into vx. That is simply au plus bv. Particular integral is simply au plus bv, where u and v both are functions of x, and as well as a and b are also functions of x. Now let us try to evaluate the values of a of x and b of x. So now first a of x. So what is a of x formula? Minus integration of r into v divided by uv dash minus vu dash dx. So minus integration of, please, what is r value? So from the given problem, r value is x into sin x. R value is x into sin x. So r value is x into sin x. And what is v value? So v value is once again here sin x. V value is sin x divided by u into v dash minus v into u dash is 1 dx. So this is given by minus integration of x into sin x into sin x sin square x into dx. So how we will evaluate this integration? So please don't come to integration by parts at this position. So first of all, we can convert sin square x into another form. So what is sin square x? Sin square theta or sin square x? So sin square x, which is equal to 1 minus cos 2x divided by 2. So please don't go for directly integration by parts. So from this stage onwards, x into sin square x like this, 1 minus cos 2x by 2. So this is given by, once again, minus integration of x into sin square x is 1 minus cos 2x divided by 2 into dx. So upon simplification, this is 1 by 2. So 1 by 2 into x means minus integration of x by 2 into dx individually. This is x into 1, x by 2, x by 2. So minus integration of x by 2 into dx. Next, minus into minus plus 1 by 2 constant. Put outside integration of x into cos 2x dx. Yes. So this is once again minus integration of x by 2 dx, minus into minus plus 1 by 2 into integration of x into cos 2x dx. Okay. So now, so evaluate the first integral minus 1 by 2 integration of x dx form. What is integration of x? Integration of x pattern, integration of x power n plus 1 by n plus 1, x power 1 plus 1 by 1 plus 1, that is x power 2 by 2. Okay, so plus 1 by 2 into, now this is the time for evaluation of integral by using by parts. So integration of x into cos 2x. So x comes under algebraic function, say first function u, cos 2x is under trigonometric function, say this is a v according to ILAT. So now apply integration of u into v. Apply integration of u into v. Integration of u into v is u into integration of v. Integration of cos 2x is sin 2x divided by dx of 2x is 2 minus, so derivative of x is 1 into integration of sin 2x by 2. Integration of sin 2x is minus cos 2x divided by 2. It is already multiplied with old 2. So this is what? Integration of x into cos 2x is once again u into v, u into x into integration of cos 2x is sin 2x by 2 minus derivative of x with respect to x is 1. Then integration of sin 2x by 2 is minus cos 2x by 2 into 2. Okay, so upon simplification we get this value is a square by 4. This is a second term x into sine 2x divided by 2 2s are 4. Then minus into minus plus, this only numerator is cos 2x divided by 2 2s are 4, 4 2s are 8. So what is ax value so far? Minus x square by 4 plus x into sine 2x by 4 plus cos 2x by 8. So now let us evaluate bx value. Let us evaluate bx value. So what is the bx formula? Integration of r into v. Integration of r into v divided by uv dash minus vu dash dx. So integration of already r value is given as x into sine x, and what is the v value? So v value is sine x. Sorry. Okay, sorry, here b of x is r into u, not r into v, r into u divided by uv dash minus vu dash into dx. So r value is x into sine x, and u value is given as already cos x. So divided by uv dash minus vu dash is 1. So now it is of the form. Now it is of the form integration of x into sin x into cos x. So we cannot evaluate directly. We cannot evaluate directly this integration of x into sin x into cos x. So in order to evaluate this particular integral, we require multiply and divide by 2. So let us multiply and divide by 2. So 1 by 2 into x into 2 sin x cos x. So now this is of the form 2 sin x cos x, 2 sin theta cos theta. 2 sin theta cos theta is sin 2 theta, 2 sin x cos x is sin 2x. So this becomes as 1 by 2 into integration of x into sin 2x dx now. Sin 2x dx now. Now let us use integration by parts once again. So x is comes under algebraic function, and sin 2x is comes under trigonometric function. So according to short form ILATE. So algebraic function x is algebraic function A, sin 2x is trigonometric function T. So clearly A comes before T. So what? A considered as first function U, T considered as second function V. Means here x considered as first function U, sin 2x considered as second function V. Now apply once again integration of U into V. Integration of U into V. So 1 by 2 into integration of U into V, U into X, integration of sin 2x. Integration of sin 2x is minus cos 2x divided by derivative of angle 2x is 2. So minus derivative of x with respect to x is 1, pre-multiple, into integration of minus cos 2x by 2. So minus 1 by 2 is constant as it is, into integration of cos 2x is sin 2x divided by 2. So the next step is derivative of 1, 0. This is just like u into integration of v minus derivative of pre-multiple x with respect to x is 1, and integration of minus cos 2x by 2 is minus 1 by 2 into integration of cos 2x is sin 2x by 2. Okay, so upon simplification we get this is minus x into cos 2x divided by 2 2s are 4. And second term, this is minus into minus plus 2 into 2 into 2. 2 2s are 4, 4 2s are 8 is the denominator. Numerator is sin 2x. Sin 2x divided by 2 2s are 4, 4 2s are 8. So this is the value of bx. So now we write the total particular integral. What is the particular integral? Ax into u of x. So what is ax value here? So ax value is minus x square by 4 plus x into sin 2x by 4 plus cos 2x by 8. It is totally multiplied with u of x cos x. Okay. So next, or possible to write as it is. So this value is minus x square by 4 minus x square by 4 x sin 2x by 4 plus cos 2x by 8. This is the total value ax into ux is only cos x here, plus bx value is minus x cos 2x divided by 4 plus sin 2x by 8 into vx value is sin x. Okay, so now hence we write the general solution or complete solution. So hence general solution of given differential equation is y equal to sum of this complementary function and complementary function and particular integrals. So write this simply sum of these CF and PI given by complete solution or general solution of a given differential equation. Okay, these are the two problems. So particularly if you observe this problem, already we did this in the class also, even though it is clearly second order linear differential equation, right hand side R is x into v case. So if they are asking in the examination, particularly solve so and so differential equation by the method of variation of parameters, then ultimately you use method of variation of parameters. Otherwise, simply they are asking like this, solve d square plus 1 into y equal to x into sin x. So without specifying any method in the examination, then you reveal this problem, solve this problem either by using previous method x into v case or by using this method of variation of parameters. So please remember, particularly this method is used to solve only second order ordinary linear differential equation with constant coefficients. That is, remember, please remember, this is used for only second order. So already we did so many problems in the classroom. So every second order linear differential equation may solve by using this method of variation of parameters. So now let us do practice at home few problems on this. So no worry, we will send some PDF problems in our group. Okay, thank you. The next session will begin within 5 minutes. Please take a short break for 5 minutes.
Yeah, good morning, everybody. Hello, all. Ravikiran here. Welcome to another lecture online. So far, we have learned many things about second order ordinary differential equations that are linear, that with constant coefficients. Now, let's see where we can apply these particular techniques. The first physical model we are discussing mass spring system. So here we have what we call a free oscillator, right? So there is no damping. There is no damping involved. Simply a mass, what you call mass and a spring, right? As you can see here, if you displace this particular mass, as you can consider here, we have considered only a particular spring, and this spring, it is attached. I mean, one end of the spring is attached to a fixed wall, and the other end of the spring, see, the other end of the spring is attached with a mass. Now, if you displace the mass from its equilibrium point and let go, as we know, the mass will oscillate up and down, and that's what we call a free oscillation. And as we know, in the perfect world, there is no friction or wind resistance. That oscillation would just continue forever with the same amplitude, isn't it? No such case is always possible. There is certainly some resistance or some kind of friction which resists the motion of this particular mass, isn't it? That's how after a certain time, definitely this particular motion leads to reaches an equilibrium position, and thereafter there may be any kind of motion, right? Now, when you are considering this particular model, what will be our question? Now, see, you have applied, you have, for example, you have just pulled this mass from its equilibrium position down by some distance, and you left it there. So then immediately it starts oscillating. Now, when this is in oscillations, after a certain time t, if you want to know the displacement of this particular mass, right? After a certain time, if you want to know displacement of this particular mass, we can calculate it exactly by modeling this as a differential equation, right? Now, see, there's a clear question. The mass is in oscillations, you see, and after a certain time, you are just trying to calculate the displacement in the spring or displacement in the mass, right? So to model this mathematically, we are just first discussing two laws from physics. The first one is Hooke's law, right? Hooke's law, it is related to what you call the spring, right? And it states that the force needed to extend or compress a spring by a distance x scales linearly with respect to that displacement. You see, when we write it mathematically, the force, this is proportional to the displacement in that spring. F is directly proportional to x, right? If you take x as the displacement in the spring here, we can write it as F is proportional to x. But see, when this spring is coming down, the force acting on that will be opposite to its correct actual motion. That's how when we replace this, we write it as F is equals to minus Kx. Understand? I'm taking this negative proportionality constant here because these two act in opposite directions. When the motion is in this, when the motion is downwards, the force acting by the spring will be in opposite direction. That's how I'm taking this as a negative proportionality constant here. And in fact, you see, this K is what we call a spring constant. Now, similar to this, you see, I'm also considering what you call Newton's second law of motion. As you know, it states that the acceleration of an object is directly proportional to the net force acting on it and inversely proportional to its mass, right? We are very much familiar with this. You see, we write it as F is equals to m into A, right? Now, see, as we know, what is this A actually? A is what you call acceleration, right? Acceleration, A is rate of change in velocity. If you take V as what you call velocity, then the first order derivative of this velocity is nothing but acceleration. And as we know, velocity is rate of change in displacement, dx by dt. That's how you can understand this A is actually second order derivative of displacement, d square x by dt square. Now, indirectly, you see, we can write F as mass times this second order derivative. Now, see, as we are with a clear idea, we are simply considering a simple mass spring system without any damping, right? Damping in the sense there is no wind resistance or there is no friction which resists the motion of the spring, right? Now, see, to model this particular system mathematically, we are just considering all the forces acting on this system, right? We are just considering all the forces acting on this system. You can just think of it this way. This is just moving up and down. So there must be certain force acting on this for, which moves it downwards. And there must be certain other force which moves upwards, which moves the spring upwards. If you just consider these two forces, we can model it mathematically quite easily. I'm just proceeding it like this, you see. Now, see, I'm just considering what you call the forces acting on this system. Now, as we know, one force acting on the system, to pull it downwards is this mass into acceleration, or we can also write it as m times d square x by dt square, where x is the displacement. The other force which acts on this, you see, it is F is equals to minus ky. If you take this k as the spring constant, I'm sorry, this is kx, right? So as we know, the force acting on the spring, in an opposite direction, it is proportional to the displacement. F is equals to minus kx. Now see, when we consider a particular system of this kind, as we discussed just before, these two forces must be equal to each other, then only what we call the system reaches its equilibrium position, right? So I'm just equating these two expressions. You see, m into d square x by dt square is equals to what you call minus k into x, right? The net forces must be equal. You see, the net forces must be zero. Obviously, whenever there is certain force which pulls it downwards, there must be an equivalent force which pulls it up, correct? So that's how the system reaches its equilibrium position. So that's how you see I'm just equating these two expressions here. M into d square x by dt square is equals to minus kx. Now see, I'm just writing everything on one side. Then you see I'm writing it like this: m into d square x by dt square is plus kx is equals to 0. Now see, for my convenience, I'm just dividing all this equation by m, right? So it is d square x by dt square plus k by m into x is equals to 0, correct? Now see, for our convenience, this k by m, I can just replace it by, let us say, some omega square. I'm taking this k by m as some what you call omega square. Therefore, you can write this equation as d square x by dt square plus omega square x is equals to 0, right? We are all wonder, you see, why I'm taking this substitution here particularly. Why did I make this substitution? Well, from experience, we know that when something oscillates back and forth, right, or else up and down, there will be a certain frequency of oscillations, let us say omega here in this case, and that would of course be the radial or radiant frequency, and that is always equal to square root of k over m. If you write this as only, if you write this only for omega, we can actually write it as square root of k by m, right? So now see, by chance, if you make the spring little stronger, if you make the spring little stronger, I mean, if you take this k little bigger, then what happens, you see, when you take this k as a little higher one, then the oscillations will be more quicker. And if you take this m as little higher than k, then you see it takes longer for the mass to change its inertia, and the oscillations will be little slower, right? So that's how you can just understand the system here. Now see, from mathematical point of view, this is a simple second order linear differential equation, that too with constant coefficients. So when you write this, in operator's form, we can write it as d square x plus omega square x is equals to 0. Remember one point here, x is, in this differential equation, x is the dependent variable and t is the independent variable. That's how I'm writing it like this, you see. And even if you write it in this way, which you are familiar with, d square plus omega square into x is equals to 0. Understand, x is the dependent variable here. And now when you solve this differential equation, we are going to get x particularly, right? We are going to find out x. I mean, x is the dependent variable. When we solve this, we are going to get this x only. And in fact, that is what you're expecting, right? You are trying to find out displacement in the spring at any time t. And you see, when we get this value x, when we substitute certain time in that solution, we'll get the required displacement, right? See, now recall, how can we solve this differential equation? Now see, this is a simple homogeneous second order differential equation with constant coefficients. So to get the solution of this, we take what you call auxiliary equation. And what it is, m square plus omega square is equals to 0. And that's how you see we can write it as m square is equals to minus omega square. And therefore, when we solve this, you see we get m values as plus or minus I omega, right? See what we are getting, complex roots. Now, since the roots are complex here, we can just write the complementary function yc, or else, in this case, it is xc, correct? Right? usually we take y as the dependent variable, but in this case, x is the dependent variable. That's how I'm writing this as xc. Then it is equals to, see how we write it? When the roots are complex here, we write it like this. You see, c1 cos omega. See, since the independent variable is t here, look at this. The independent variable is t. That's how I'm now writing this as c1 cos omega t plus c2 sin omega t. Now see, this is the general solution. In fact, since this differential equation is a homogeneous differential equation, as we know, complementary function itself is the solution of this differential equation. That's how, instead of taking this as xc, I can take it as only x. Right? Now see, this is the equation. I mean, this is the solution from which you can calculate the displacement in the spring at any time t. Right? But you can wonder, you see, there are two other constants. What are these two? C1 and C2. See, when you consider a particular system, certainly there will be other conditions, right? So using those two conditions, we can actually evaluate these two arbitrary constants, and thereby we can find out the what you call exact solution for this differential equation. And when we get the exact solution, we can actually calculate what you call displacement, the actual displacement in the spring at any time t. Right? Now see, when we begin this, before I think the first few seconds when we begin this discussion, we have actually ignored damping. Right? What do you mean by damping there? You see, I've simply ignored the friction or the wind resistance, when it is in oscillations. But you see, there are few instances where wind or there may be some other friction which resists the motion of what you call the mass or spring. But see, we cannot simply ignore that. There are possibilities where wind may also resist what you call this motion in the spring. So if you just consider what you call that damping conditions also, then see what happens when there is a damping during the motion. So damping actually, if you consider a mass m, right? If you have attached this particular mass to the spring, then the force, I mean the wind force or else the frictional force, that force is always proportional to the velocity of this particular spring. And see, when x is the displacement, we can write it as F is proportional to velocity, in the sense it is dx by dt. Now, this frictional force is always proportional to what you call, velocity here, right? I mean, if the spring is oscillating with a little higher velocity, if it is moving with a little higher velocity, then equivalent to this, there will be a force which is proportional to this one, right? An equivalent force will resist this. If it is moving with a little lower velocity, there will be an equivalent force which to resist it. Correct? And that too, you see, when the spring is coming down, or else when the mass is moving downwards, then there will be a force to resist this, which moves against to this, right? And if it is coming, if the spring itself is moving upwards, then what happens? You see, if the spring is moving upwards, then there will be a resistive force which moves downwards, right? Then only, when these two move in opposite directions, then only we can, the wind may resist the what you call this mass, right? So keeping these things in view, you see, when I model this, the damped force is always proportional to this velocity. And if I replace it by this, you see, F can be written as, because those two move in opposite directions, I'm replacing it again by a negative proportionality constant. I'm taking this time it as minus R into dx by dt. Right? Now see, if you consider a system including damping, which involves damping also, then if you again model it mathematically, see now, these are the forces acting on this. One force which moves downwards is F is equals to ma, right? This moves, the mass moves, when we consider this mass, this force, we'll get it this way. And the other two forces which act on the system, these two. One is due to spring, F is equals to minus kx. And the other one is due to what you call damping, which is minus R into dx by dt. Right? Understand, this is the force which pulls the mass downwards. And these two are the forces which resist the first one. Right? So when you consider the net force, these two must be equal. That's how you see, when we consider damping, we just equate these two things. Instead of A, I'm writing it as a second order derivative, m into d square x by dt square, and this is equal to sum of these two forces. You see, these two forces move together, right? Whether it is due to spring or whether it is due to what you call damping. Now see, that's how we just add these two, minus kx minus r into dx by dt, right? So this is the force which pulls the mass downwards, and these two together, the mass which pulls it upwards, correct? That's how I'm just equating these two. Now if you can write all these things on one side, we can just write it like this: m into d square x by dt square plus r into dx by dt plus kx is equals to 0. And see, now as usually as we did in the previous case, I'm just dividing all these terms by m, so that we can write it like this: d square x by dt square plus r by m into dx by dt plus, again here you see, k by m into x is equals to 0. Now see, as we assumed a few minutes ago, we can just replace this k by m by omega square. And if you just, for instance, if you take this r by m by some 2b, the new differential equation which you get here in this case is this: d square x by dt square plus 2b into dx by dt plus omega square x is equals to 0. Right? See, again, this is also a second order linear differential equation with variable, what you call constant coefficients. That too, you see, it's a homogeneous differential equation, no right hand side force, right? Now see, when you consider this type of differential equation, we know, again, we can calculate what you call auxiliary equation for this. We can find out the complementary function as well. Now see, from that complementary function, in fact, since it is a homogeneous differential equation, that complementary function itself is the general solution of this differential equation, right? Again, by solving this equation, we can find out displacement in the spring at any particular instance of time, right? So I'm just summarizing this simple idea here. Now see, when it is a model of free oscillations, when there is no damping, you have just considered a spring and a mass, then the differential equation which comes out from this is d square x by dt square plus omega square x is equals to 0, where k by m, actually where omega square is what you call k by m. And in case if you have considered damped oscillations, right, when you have considered damped oscillations, as we discussed till now, so this is the differential equation which you get it from this. Right? So when you consider damping here, this is the differential equation you get. See, there are few other cases actually which we are not discussing as part of our syllabus. Understand forced oscillations. See, when it is in motion, if there is an external force acting on the system, then see that external force we consider here on the right hand side, which leads to mathematically a differential equation with some other right hand side function, right? We had already seen some cases where there exists some right hand side function. We had discussed different cases for finding the particular integral. Now see, when we have some external force acting on the system along with damping, then see, we get this differential equation. And see, we are applying some external force, but there is no damping. In that case, you see, we get this as the differential equation, right? So exactly these things, looking at the problem now, we need to recognize what is the differential equation. Understand, when there is only certain spring and you are considering a mass there, you are simply ignoring damping. In that case, we consider this as the differential equation. And if there is spring and mass as well as what you call a damping, right? If you are considering the air resistance, for example, then in that case, you take this as the differential equation, right? And anyway, we are not discussing much on these external forces, but looking at the question, you need to identify. Along with these things, if you are also applying some additional force on the system, then we take that additional force on the right hand side, and thereby we get this as the differential equation, right? And you see, this is other differential equation when we ignore what you call damping, right? So these are the four differential equations we use normally in solving the problems in simple, right? Now let us take few problems, and you need to now identify which differential equation which will get from the information given in the question. I'll just move on to a question like this. Let's look at this question. Look at this question. Yeah. See what you are given. A mass of 4 lb is suspended from a light elastic string of natural length 3 feet, extends it to a distance of what you call 2 feet. One end of the string is fixed and a mass of 2 lb is attached to the other. The mass is held so that the string is just unstretched and is then let go. Find the amplitude, period, and maximum velocity of the ensuing simple harmonic motion. I must tell you one point here. Being you're all engineering students, you must be aware of what are these three things: amplitude, period, and maximum velocity. See, for example, as we discussed till now, for some differential equation, you see, if you get solution as this, something like C1 cos omega t plus C2 sin omega t, right? When you substitute the conditions given in the question, we may get the solution of this differential equation as something like a cos, let us say omega t. Probably some of these two, one of these two is got already cancelled, right? Or else, if not this, we may get it as something like omega t plus phi. There may be a kind of phase difference, as you know. Now, see, in this case, if this is the solution which you got from some physical system you have considered, what this A represents, what this omega represents, you must know, right? See, A represents what you call amplitude of this particular system, or else amplitude in the spring motion. Then omega is the frequency, as you know, correct? And period means, in fact, even mathematically we can discuss this. Period is, as we know, it is 2 pi by omega, correct? And then the maximum velocity is, you see, when we normally velocity means differentiation, dx by dt. Even when you differentiate this, you see, you will get this a into, when we differentiate cos, we'll get a minus sign, and also we get a omega. So whatever the a omega you get here, we take this as the maximum velocity here, right? So now, keeping these formulae in view, we need to calculate amplitude, period, maximum velocity, all these things. And see here, you are getting some simple harmonic motion. When it is a simple harmonic motion, as you know, we are considering only a spring and a mass, right? See, in the question, there is no information about any, medium resistance, right? So there is no wind resistance or there is no additional friction force there. That's how we are considering only a spring along with a mass. Now, see, there is another information given in the question. Let us also see that. Look at the first statement of the question. When you attach a 4 lb mass, now see, the spring is extended to 3 feet, right? Understand it this way. Spring is attached to one end here. You are adding a spring here, at the other end of the spring, you are adding, for example, a mass of 4 lb. Now, when you add a mass at this end, this spring, it is pulled down by, let us say, you are given it as 2 feet, right? You are given it as 2 feet. Now, see, it is at this position. Now, when it is moving down, what are the forces acting on that? There are two forces acting on that, you see, which is m into g, right? This is the force due to gravitation. M into g is equals to the force which acts on that due to due to the spring, which is minus k minus k into, you see, the displacement. Displacement, you see how much displacement you got here? It is 2 feet. So I'm just taking it as k into 2 here, right? So when it is in this system, the forces acting on this particular system, when you equate them, one is force due to gravitation, which is equal to m into g, and the other one is, due to what you call spring, this restoring force which acts by the spring. The restoring force, it is equal to k into the displacement x. When we add this much of mass, the displacement you are getting is 2 feet. That's how you can see mg is equals to minus k into e. And what is the mass you are given in this? You see, mass, you are actually attaching a 4 lb of mass. That's how it is 4. And what may be the acceleration due to gravity? Look at this. The distance is given in feet. Normally, when it is g, we take it as 9.8 meters per second square. But since you are given it in terms of feet here, I'm taking this as what you call 32 feet per second square. I'm just converting meters into what you call feet. That's how, see, I'm taking here this as 32, and this is equals to 2k here. Then see, this implies we can just write k is equal to, if we just simplify this, we'll get k as 64, and this is lb for feet. This is the restoring constant here. Now see, as you can see, this is just an information what you're given in the question, but actually you are applying a mass of 2 lb. You are actually applying a mass of 2 lb, and due to this there will be an equivalent in what you call, then there will be an equivalent enhancement in this particular spring, right? So you can just think of it this way: when you add a mass of 4 lb to this spring, you are getting a distance, the spring is extended to a distance of 2 feet. Similarly, when you add a mass of 2 lb, half of that, so this extends the spring by again 1 feet. So how can you calculate this? See the elongation in this. I'm just taking the same story again. When you add now, instead of 4 lb, if you now add a mass of 2 lb here, then how much elongation we get in this spring, right? Now to calculate this, you see, m into g is equals to k into, let us say the elongation is e, right? We are actually continuing the problem with actually this particular mass, right? You are given some mass here just to calculate what you call this restoring constant. So when it is mg is equals to k into e, see, we got all these things already. M is, now you are attaching a mass of 2 lb, and as we know, g is 32 feet per second square, and k we got it as 64 here, and this e is to be calculated. And you can see here 64, 64, you can just cancel it, and we get the elongation as exactly 1 feet. Understand it this way: when we attach a mass of 4 lb, we got the elongation as 2 feet. And now when we attach this particular mass, only 2 lb, now corresponding to this, we get the elongation as exactly 1 feet. Now see, all this is just an information. Now just recall what differential equation we have to use here. Understand, there is no damping force, so we need to use the differential equation, this one, d square x by dt square plus omega square x is equals to 0, right? When there is no damping, this is the differential equation we use in this case. Now see, what is x here? X is the displacement which we need to calculate, and here omega square is, as we know, k by m. Let us just calculate what is this omega square here in this case. As we know, you see here k, we got it as 64, and mass you are attaching is exactly what you call 2 here, 2 lb, so that you can see omega square becomes simply 32, and that implies, you can see, the differential equation we use in this case is d square x by dt square plus 32x is equals to 0. Now see, this is a simple second order linear differential equation. By solving this, we are going to find out what you call the displacement in the spring. I'm just continuing it like this. You see, this is the differential equation you are given: d square x by dt square plus 32x is equals to 0. Now see, I'm just writing the auxiliary equation, which is m square plus 32 into x is equals to 0. And see, if you just, I'm sorry, when I write auxiliary equation, it is only m square plus 32 is equals to 0. Correct? Then see, if you find out the roots of this equation, m square is equals to minus 32, and thereby you can write m is equals to plus or minus square root of minus 32, right? So when it is plus or minus 32 minus 32 here, we can actually write this as plus or minus 4 root 2 I, right? So clearly the roots are complex. When the roots are complex, as we know, we can write the complementary function xc. See, the x is dependent variable in this case, xc as, right, see, we can write xc as c1 cos 4 root 2 t, because the t is independent variable, plus c2 sine 4 root 2 t. Now see, this is what you call complementary function for this particular problem. Now see, we don't want to get the solution in terms of c1, c2 here. In fact, though I'm writing it as complementary function, as we know, since it is a homogeneous differential equation, we can take complementary function itself as the general solution. That's how I'm now writing x is equals to C1 cos 4 root 2 t plus C2 sine 4 root 2 t. Now see, this is the solution I'm getting in this case. When this is the solution, I need to now calculate C1 as well as C2. Now see, to calculate these two constants, we need two conditions, right? Let us just see what are these two conditions. Let's just go back to the actual question. Now see, the mass, there is a statement in this question here. The mass is held so that the string is just unstretched and then let go. See, you have just attached a mass and then you are not allowing it to oscillate itself. You are still carrying that, right? It is about to take oscillations. So when you attach a mass here, just now we have calculated, you see, when you add a mass of 2 lb here, it is elongating for exactly 1 feet. That's how the initial displacement in the spring is exactly what you call 1 feet here. That's how you see I'm taking this as my first condition here. So when time t is 0, the initial displacement x will be now exactly 1 feet. And see, you are not initially allowing it to oscillate itself. You are not, you are just about to leave it, right? That's how the initial velocity at time t is equals to 0, the initial velocity dx by dt becomes simply 0, because they're all free oscillations, right? So now using these two conditions, we are going to find out C1 as well as C2. Now see, if I use the first condition, right? If I use this first condition, x is equals to 1 when time t is 0. See what you get here, x is equals to 1. When you substitute time t is equal to 0, C1 into, if you take t is equal to 0 here in this, cos 0 becomes simply 1 plus C2 into, you see, when you substitute t is equal to 0 in the second expression, we'll get it as sine 0 as simply 0. That's how you can see C1 is equals to directly 1, right? Then what happens to x? You see, x is equals to now just cos 4 root t plus this one. I'll also find out that x is equals to, it is now instead of C1, I'm just taking what you call 1 here. So it is cos 4 root 2 t plus C2 into sine 4 root 2 t here. Now, let me just use the second condition, and to use the second condition, I need to differentiate this. So when I differentiate this, you see what happens? Dx by dt is equals to, I'm just differentiating this. Now, when we differentiate this, as we know, differentiation of cos is minus sign, right? So that's how we'll get minus 4 root 2 into sine of 4 root 2 t plus, when we differentiate this, as we know, 4 root 2 c2 into differentiation of sign is, cos 4 root 2 t. Now see, if you use the second condition is what? Dx by dt is 0 when t is equals to 0. So I'm just taking dx by dt is equal to 0 on the left hand side. And if I substitute t is equal to 0, because of this sine function, this becomes completely 0 plus, when you substitute t is equal to 0 in the second expression here, this cosine function becomes simply 1. That's how here we get it as only 4 root 2 c2. And from this you can see we'll get the value of c2 is equals to 0. Right? See what we got? C1, we got it as 1 and we got C2 as 0. Now let us substitute these two values in the solution what we got earlier. Right? See, the solution we got is x is equal to C1 cos 4 root 2 t plus C2 sine 4 root 2 t. And here in this, I'm substituting C1 is equal to 1 and C2 is equals to 0. That's how you can see we get the solution x as only this much. Wait a second. Now see, when we substitute these two conditions here, we get the solution as only x is equals to cos, I'm just writing only this, cos 4 root 2 t. Right? The other one we got it as simply 0. Now see, this is the solution we got. And now just recall what we are asked to find. We are asked to find exactly 3 things. One is amplitude. Right? As we know, normally amplitude is what you call the maximum displacement. Now, when this is the displacement at any time t, what will be the maximum value for this? It is the coefficient of this cosine function. As the coefficient of this cosine function is exactly 1, the maximum displacement will also be 1. And therefore, the amplitude, we normally take it as A, and that becomes exactly 1 feet. Right? And now if you calculate its periodicity, or else if you take it as period, whatever it is, okay. Now, if you calculate its periodicity, since it is something like cos omega t, right? It's a cosine function, even mathematically speaking. When it is a cosine function, its period will be, as we know, 2 pi by omega, which is equals to 2 pi divided by, see the omega is now 4 root 2. I'm just substituting that 4 root 2 here. 4 root 2. This is equals to, if you simplify this, it is what you get here, you see pi divided by 2 root 2. Right? I don't want to write any units there. And the other thing what you're asked to calculate here is maximum velocity. Right? See, what may be the maximum velocity? You see, as I told you already, maximum displacement, which is amplitude multiplied by this frequency, is nothing but maximum velocity. That is equals to, you see, the amplitude what we got is exactly 1 multiplied by the frequency what you have here is exactly 4 root 2. So this 4 root 2, if you want to write its units, it is exactly feet per second. So this is how you can just calculate displacement at any time t, and as well as these three conditions as well, right? So that's how you can solve any problem in mass spring system. Now see, for convenience, sir. Okay, right? So I'm just stopping this with only one problem. Now the next faculty, Dr. Balram Krishna sir, will continue the next application. Please stay online.
Good morning to one and all. This is Dr. Balram Krishna, giving you the glimpses of applications of second order linear differential equations in regard with the electrical circuits. Generally, the linear differential equations with constant coefficients find their applications the linear differential equations with constant coefficients find their applications in electrical, mechanical, and other linear systems. The formation of a differential equation for an electric circuit depends on the following laws. See, if we denote I as the current and Q the charge in the condenser plate at any time t, then the current I is denoted as dq by dt, the rate of change of charge with respect to time. And the voltage drop across a resistor is given as V equal to IR, or generally we denote it as RI. Voltage drop across an inductor is E equal to L into di by dt, where I is dq by dt, hence it can be taken as L into d square q by dt square. And the voltage drop across a capacitor is given as V equal to Q by C. Knowing all these things, and as already you know about Kirchhoff laws, Kirchhoff voltage law says that the algebraic sum of the voltage drops in each part of any electrical closed circuit, which is equal to the resultant electromotive force EMF in that circuit. And as well as the current law says that at a junction or node in a circuit, the current which is coming is equal to the current going. The interconnection for these LC circuits or in any circuit, the interconnection of simple electric device in which there is at least one closed path for current to flow, it is called as electric circuit. The circuit, when it is in the switched form from one condition to other condition by change in the applied source or a change in the circuit elements, which is a transition period during which the branch current and voltage change from their former values to the new ones. This period is called as a transient period. And after that transient period has passed out, the circuit is said to be steady state. With respect to our linear differential equations, which describes the circuit, will have two parts to its solution. As in mathematical sense, those two parts are complementary function and as well as particular integral. Here, the complementary function corresponds to the transient period and the particular solution corresponds to the steady state. The value of voltage and current during this transient period known as a transient response, which we will be giving as complementary function. And the value of voltage and current after transient period has died out. That means after the changes, the steady state response, which we will be giving in the resultant form as particular integral of the differential equation. And altogether, those complementary function and particular integral put together will be getting the general solution. And if you observe here in this LC circuit, considering that an electrical circuit containing an inductance L and the capacitance C, here we are getting the I as the current and Q as the charge in the condenser plate at any time t, so that the voltage drop across the inductor L is given as L into di by dt, as we have discussed earlier. So L into di by dt, this I is nothing but dq by dt. Therefore, d by dt of dq by dt, which comes as L into d square q by dt square. And the voltage drop across capacitor C is V equal to Q by C. As there is a, you can see in this circuit, there is no applied electromotive force EMF in the circuit. Therefore, by Kirchhoff laws, first law, we have LD square Q by dt square plus Q by C equal to 0. Or we can have some mathematical concepts, mathematical operations, dividing with L and writing 1 by LC as mu square. This can be written as d square Q by dt square plus mu square q equal to 0. So this equation represents free electrical oscillations of the current having a period 2 pi mu, and that is given as 2 pi into root LC. And for LCR circuit, the same. Here we will be having some resistance and inductance and as well as capacitance. Here, since the voltage drop across L, C, and R are respectively L d square q by dt square, q by C capacitance, and the resistance, that is d R into dq by dt. Again, by Kirchhoff laws, we are having the equation as L d square q by dt square plus R dq by dt plus q by C equal to 0. Whenever resistance is given, the second term will be getting as R dq by dt. On writing R by L as 2 lambda and 1 by LC as mu square, the equation can be written as d square q by dt square plus 2 lambda into dq by dt plus mu square q equal to 0. Suppose in that circuit, the equation for LC circuit, which is given taken as L into d square q by dt square plus q by C equal to 0. If some electromotive force of P into cos nt is introduced, the equation becomes as LD square q by dt square plus q by C equal to P into cos nt. It's a forced oscillation. Some electromotive force is being introduced. Thus, by writing again with 1 by LC equal to mu square, the equation becomes like this: d square q by dt square plus mu square q equal to P by L cos nt. Thus, in this condenser placed in series with the source of electromotive force, which is given as P cos nt, and discharging through a coil containing inductance L, is an electrical analogous. It's similar to that of forced oscillations of mass m on a spring. And here is some LCR circuit, which is having again electromotive force of P cos nt, which is given as L d square q by dt square plus R dq by dt plus q by C equal to P cos nt. And here we will be getting the equation after some mathematical operations: d square q by dt square plus 2 lambda into dq by dt plus mu square q equal to P by L cos nt. So you need to understand, whenever electromotive force is given, the right hand side function is present. That means when there is no electromotive force, in the case of non-presence of electromotive force, we will be having only the left hand side part of the equation, and hence it is considered as a homogeneous linear differential equation, and no need of finding the particular integral in regard with the P cos nt or whatever the function that is given on the right hand side in the position of electromotive force. So with this, let us go with one example problem. I mean, a problem which may consist of electromotive force or may not. First, simply I am taking a simple problem, the differential equation for a circuit in which self-inductance and capacitance, which are neutralize each other, is that is given as L d square I by dt square plus I by C equal to 0. The differential equation is given. Then we need to find the current I as a function of t, given that I is the maximum current when I equal to 0, and when t equals 0, initially I equal to 0. So what we have given is 1 second, please. Yes. Given the differential equation, what differential equation is given? L into d square I by dt square plus I by C equal to 0. That can be taken as L into d square plus 1 by C into I equal to 0. LD square plus 1 by C into I equal to 0. Generally, in our mathematical problems, we will be taking as f of d into y equal to 0, but it is the variable is y. I. And the auxiliary equation now we can write as LD square. I'm not writing in terms of M, just writing in the same form, LD square plus 1 by C equal 0, and writing the solution for in D form also in itself. LC D square plus 1 equal 0, or D square equal to 1 by minus 1 by LC. That means D can be written as plus or minus I by root LC. Now, it is a complex root, therefore we can write the complement function as I of t equal to C1 cos t by root LC plus C2 sin t by root LC. Because into e power 0 into t, that becomes as 1 before the term. The general form of complement function when the roots are given as complex roots, that is e power 0 into x into C1 cos m2x plus C2 sin m2x. Here m2 is nothing but 1 by root LC. So thereby the complement function is given as C1 cos t by root LC plus C2 sin t by root LC. As there is no electromotive force present, the right hand side is 0, thereby we don't have any particular integral, and hence the general solution itself, it is I of t is given as in this form, C1 cos t by root LC and something. Now, the other thing of the problem says that when t equals 0, when the initially the current is equal to 0, we make use of that one and we'll find out the values of constants C1 and C2. Given that, what is given? I of 0 equal 0. Let me explain once again. When t equals 0, I is given as 0. Therefore, I of 0 equal to 0. That is, I of 0 is equal to C1 cos 0. When t equals 0, t by something, 0 by something 0. Therefore, t by root LC, that becomes 0, plus C2 sin 0. That is equal, that implies what we can, sin 0 is 0, cos 0 is 1. Therefore, C1 equal to, I of 0 is given as 0 only. Therefore, C1 equal to 0. Therefore, the original complement function becomes as I of t equal to C1 is 0, therefore the terms cuts off, and C2 sin t by root LC. I of t equal to I into sin t by root LC. Here I need to explain the thing as for simple harmonic motion, the equation for SHM, the equation is given as d square x by dt square plus omega square x equal to 0. For this, the solution is given as x equal to a times cos omega t or omega x, like that, omega t, where this a indicates amplitude or maximum displacement. Thereby, comparing this solution to our present solution, I of t equal to I into sin t by root LC. If you compare these two, we'll be getting the maximum current. I is the maximum current. I is the max current, that is given as C2 equal to I, or I equal to C2. The maximum current which is going in that circuit is C2. Let me go with one more problem. A condenser of capacity C discharged through an inductance L and resistance R in a series. The charge at Q at time t satisfies the equation LD square Q by dt square plus R dQ by dt plus Q by C equals 0. Given that L Inductance is given as 0.25 Henries. Resistance is given as 250 ohms. And capacitance is given as 2 into 10 to the power minus 6 farads. And that when initially, when t equals 0, the charge q is given as 0.002 coulombs. And the current dq by dt equals 0. With all these information, we need to obtain the value of q in terms of t. So already the differential equation for which the condenser of capacity C is discharged through the inductance L and resistance R is given as L d square q by dt square plus R dq by dt plus q by C equals 0. Let us consider the equation, the differential equation as L d square q by dt square plus R dq by dt plus q by C equal to 0. Or this can be written as L into d square plus RD plus 1 by C into Q equal to 0. Now taking value for D equal to minus R. Yeah, just I'm using quadratic equation rule, minus R plus R minus square root of R square minus 4AC. That means 4L by C whole by 2A. 2A means 2 into L. Minus B plus R minus square root of B square minus 4AC by 2A formula I have used it. With respect to this one, D is given as like this. Now we will substitute all the given values. L is given as D equal to, L is given as, let me write down all the values here. L equal to 0.25 and R equal to 250 ohms. C equal to 2 into 10 to the power of minus 6 farads. So by substituting in this one, I'll be having minus R minus 250 plus R minus square root of R square. 250 square means it comes 62,500 minus 4 into L. L means 0.25 by C. C means 2 into 10 to the power of minus 6 whole by 2 into L. 2 into 0.25. Altogether, if you simplify this one, you will be getting as a minus 500 plus or minus I into, I'm not just going to the simplification, just giving you the answer. One can see on your own. I into 1322.87. You can verify yourself. The answer will be getting D as minus 500 plus or minus I into 1322.87. Therefore, I can write the charge Q of t as e power minus 500t into C1 cos M2. M2 means 1322.87 t plus C2 into sin M2. M2 means 1322.87 into t. Now we need to use the condition. Let me go back and show you the question. When charge Q is 0, when current dq by dt equals 0 initially, we need to find out the value of Q in terms of t. Therefore, given Q equal to 0.002, which we have not used it so far, and the dq by dt is also equal to 0 when t equal to 0. So when we substitute t equal to 0 in this one, we'll be getting Q as 0.002 coulombs. And that of the differentiation of this charge Q is equal to 0 when t equal to 0. Let me do that one. So dq by dt equal to minus 500. Just UV formula I'm using, minus 500 into e power minus 500t into C1 cos 1322.87 into t plus C2 sin 1322.870 plus e power minus 500t. I am now doing for differentiating for the second function. It is minus C1. For cos, it is minus sign. Therefore, minus C1 sine 1322.870 into inner function differentiation, that is 1322.87 plus C2 for sine, it is cos. C2 cos 1322.87 into t, and the inner function differentiation, if it is 2x, it comes to 2 into, thereby into 1322.87. Now in this one, we know that dq by dt equals 0 when t equals 0. Both conditions we need to consider. When t equals 0, q equals 0.002, as well as when t equals 0, the derivative dq by dt is also equal to 0. So thereby using these two conditions, I am writing when t equals 0, dq by dt equal to 0. That means I am writing minus c, minus 500 c1 plus 1322.87 c2 equal to 0. That means C1 will be coming as 0.002, because what we are doing, we are substituting t equals 0 in q of t. By substitution, t equals 0 substitution. Let me go to next one. Now 1322.87 t is equal to t into C2 equal to 500 C1, or that equal to 500 into what is C1, 0.002, which comes to C2 equal to 500 into 0.002 by 1322.87, which comes around 0.0007559. So by substituting the given conditions, we need to find out C1 and C2. Therefore, after finding those two values, I am writing Q equal to e power minus 500t into what is C1, that is 0.002 cos t, cos 1322.87 into t, plus C2. C2 is 0.0007559 into sine 1322.87 t. So by using the given conditions, we need to find out the parameters, constants in the present in the solution. C1 and C2 should be found out with the given conditions. Okay. With this, let me complete the today's class. Have a good day. Thank you.
Let's see. Thanks for attending the class. If you have any questions, please post them in your class groups. Thank you.